Welcome to the deep dive. Today, we're tackling a really interesting challenge in the world of machine learning. How do we know how good our models are when we don't have all the answers?
Yeah, specifically, what happens when some of the true results, the labels, are missing when we're trying to evaluate performance?
It's a fantastic and honestly often overlooked question.
It really is. We put
Yeah.
so much effort into building these complex ML systems, but if we can't get a clear, accurate picture of how they actually work in the real world, where data is messy and stuff goes missing,
Then our understanding is just fundamentally incomplete.
right, flawed.
Exactly. And our mission today is to explore some pretty cutting edge thinking on this. We're going deep into a research paper called Model Evaluation in the Dark: Robust Classifier Metrics with Missing Labels.
So our main source is this paper itself, and they propose a really novel way to assess classifiers even when we don't have all that ground truth data.
Okay, and one of the first big points they make is that the usual approach, like tossing out the data points with missing labels,
Uh-huh. List-wise deletion?
right, that can really skew the results.
Yeah, especially when the missingness isn't just random. They call it missing, not at random, or MNAR.
MNAR. Okay.
And the key insight there is, if the reason a label is missing is tied to the thing you're trying to predict, well, then looking only at the complete data gives you a totally misleading picture.
Okay, so let's unpack the core idea from the paper then. They introduced this method called performance estimation by multiple imputation, PMI.
PMI.
Yes.
Right. And they also offer a Gaussian approximation of it called PMI Gauss.
PE on gas. And the goal of these techniques is to give us a good estimate of classifier performance, using standard metrics like precision, recall, and ROCAUC,
Area under the receiver operating characteristic curve, yeah.
even when we have those gaps in our evaluation labels.
And what's really fascinating about PMI and PMI Gauss, I think, is that they don't just spit out a single number.
Oh.
No, they give you a probability distribution. Think of it like a weather forecast, giving a chance of rain, not just yes rain or no rain.
Okay, so it shows the uncertainty.
Exactly. It reflects the uncertainty caused by those missing labels.
Yeah.
So you get a much richer sense of the possible range of your model's performance.
All right, let's dive into the heart of it then. This problem of missing labels during evaluation. The paper kicks off by outlining the different ways data can go missing. Can you walk us through those?
Sure. So they highlight three main types.
Mm-hmm.
First up is missing completely at random, or MCR.
MDR.
Yeah. In this case, whether a label is missing has absolutely zero connection to the data itself. Not the data you see, not the data that's missing. It's like purely random chance, like someone literally flipped a coin.
Got it. Pure randomness. What's next?
Next is missing at random, or MAR.
MAR.
Okay. Here, the fact that a label is missing does depend on other data you have observed, but crucially, it doesn't depend on the actual value of the missing label itself.
Can you give an example?
Sure. Think about a survey asking for income. Maybe men are generally less likely to answer that question than women. So the missingness not answering depends on gender, which you observe. But it doesn't depend on the specific income level that the man didn't report.
Right, so there's a reason why it's missing, linked to observed data, but not the missing value itself. Got it. And the third type, missing not at random. That's the tricky one.
That's the really tricky one, yes. MNAR, missing not at random. This is when the fact that the label is missing is related to the unobserved missing value itself.
Uh-oh.
Yeah. So maybe in a study about, say, treatment effectiveness, patients who are doing very poorly might be less likely to show up for follow-up appointments where their outcome would be measured.
Ah, so the missingness not showing up is directly linked to the value you're trying to capture. Poor outcome.
Exactly. And the paper uses some neat graphical models, figure 1, I think, to show these different causal links visually.
And as the paper points out, in the real world, it's often super hard to know for sure which mechanism is really happening. We don't always know why data is missing.
That's a huge challenge. And it loops right back to why just ignoring missing labels, that list-wise deletion, is so risky.
Because if it's MAR or MNAR.
Right. If it's not MNAR, then the data you do have labels for might not be representative of the whole picture at all. And your performance estimates could be seriously biased.
Okay. Can you give us some concrete, real-world examples where this happens? Where you'd evaluate a model but be missing labels?
Absolutely. The paper mentions a couple. Think about detecting fraudulent credit card transactions.
Okay.
Your model flags a transaction as suspicious, makes a prediction, but confirming if it was actually fraud, That takes investigation, sometimes days or weeks.
So right after you deploy the model, you want to see how it's doing, but for many transactions, the true label fraud or not fraud is still pending. It's missing for your immediate evaluation.
Exactly. You need to evaluate quickly,
Mm.
but the ground truth lags behind.
That's a great example. What's another one?
How about recommender systems, like on a shopping site or streaming service?
Yeah.
The system recommends items. You want to know, did the user click? Did they buy? Did they watch? That's your label. But not everyone interacts. Some people just ignore the recommendations entirely.
And maybe the people who ignore them are the ones who got bad recommendations?
Precisely. So the likelihood of providing feedback or even interacting might be related to the quality of the recommendation itself. That smells like M&AR. If you only evaluate based on the interactions you did get, you're missing a potentially crucial part of the story, the users who disengaged.
So throwing out data with missing labels.
Yep.
Yeah, doesn't sound like the way to go. Now, the paper talks about naive estimation. What are some of the simpler ways someone might first try to deal with this, and why don't they really work?
Well, one really basic idea is just brute force. If you have, say, 10 missing labels, you could theoretically list out every single possible combination of zeros and ones for those 10 spots.
Okay, that sounds like a lot.
It is. For each combination, you calculate your performance metric. But, like the paper says, the number of combinations explodes exponentially, 2 to the power of the number of missing labels.
Oh, wow. So even with like 30 missing labels, that's over a billion combinations.
Exactly. It becomes computationally infeasible almost immediately. Totally impractical.
Right. Okay, so brute force is out. The paper also mentions optimistic and pessimistic bounds. What's that about?
So, for any metric, you can calculate the absolute best case and worst case scenario for those missing labels.
Wow.
For the optimistic bound, you just assume your classifier got every single missing label correct. Calculate the metric. For the pessimistic bound, you assume it got every single one wrong. Calculate the metric again.
Okay. So you get a range. The score if everything went perfectly for the missing ones, and the score if everything went terribly.
Exactly. But the problem, and figure 2 in the paper shows this really well, is that this range is usually massive.
Like how much?
Often, it can span almost the entire possible range of the metric. If your precision could be anywhere between, say, 0.1 and 0.9, that's not very helpful, is it?
No, not really. It tells you the absolute outer limits, but gives you no clue about what's actually likely to be happening.
Precisely. It's just too wide to be useful for practical decision-making.
Which brings us then to the core proposal of the paper. Performance estimation by multiple imputation, PEI. How does this work? What's the big idea?
Okay, so PEI, which they lay out in Algorithm 1, takes a different approach. Instead of trying every possibility or just looking at the extremes, it uses random sampling.
Sampling.
Yes, for each data point that's missing its true label, PEI randomly generates a potential label, a 0 or a 1.
Okay, how does it decide whether to generate a 0 or a 1?
It uses a Bernoulli distribution. Think of it as flipping a weighted coin for each missing label. The weight of the coin determines the probability of getting a positive instance.
A weighted coin flip. Got it. And what determines the weight? The parameter of that Bernoulli distribution.
That's the crucial part. The paper calls this parameter pi. It represents the conditional probability. P-true label equals 1, given the features x, and given the label is missing M1.
Okay, so pi is basically our best guess for the probability that this specific missing label should actually be a 1.
Exactly. It's the estimated probability of being positive, given what we know about the data point and the fact its label is missing.
And how do we actually figure out these pi values in practice? The paper suggests a few ways.
Yeah, the main way they focus on is using a well-calibrated model.
A well-calibrated model. What does that mean exactly?
It means the probabilities the model outputs actually reflect the true frequency of events. So if a well-calibrated model predicts a 70% chance of rain, then over many days where it made that prediction, it should actually rain about 70% of the time.
The predicted probability matches reality.
Precisely. The paper mentions using something called a scaling binning calibrator. It's just a specific technique to tweak a model's raw outputs to make them better calibrated.
So we take our machine learning model, calibrate its probability predictions, and then use those calibrated probabilities as the pi values for the corresponding data points with missing labels.
That's the main idea, yes. You're using the model's own calibrated prediction about a data point to inform the imputation of its missing label.
Okay, that makes sense. What if we don't have a well-calibrated model or we want to make fewer assumptions? Are there other ways?
Yes, the paper mentions using the maximum entropy principle, or max max set.
It's
It's a
secret.
principle that says, basically, if you have limited information, your best bet for a probability distribution is the one that's most spread out or makes the fewest assumptions, while still matching what you do know.
So how does that apply here?
Well, if you know absolutely nothing about the missing labels, Maxent says the most unbiased assumption is that 0 and 1 are equally likely. So you just set pi to 0.5 for every missing label. Maximum uncertainty.
Okay, 50-50 if you know nothing. What if you know a little bit more, like maybe the overall rate of positives in the training data?
Good point. If you know the overall base rate of positive examples, say n plus divided by n,
Yeah.
total examples, you can use that as a constraint. Maxent then tells you to set pi equal to that base rate, n plus n, for all missing labels.
So you use the overall average probability.
Exactly.
Hmm.
But the paper really stresses that your choice of how to set pi matters a lot. The quality of your final performance estimate distribution really depends on having reasonable pi values.
Right, the imputation is only as good as the probabilities you feed into it. Makes sense. So once we have these pi values, PEMI involves sampling labels repeatedly.
Yes, you run this process many times. Each time you generate a complete set of labels, original plus imputed ones, calculate your performance metric, like precision or recall, and you store that value. After doing this, say, thousands of times, you have a collection of metric values.
And that collection of values gives you an empirical distribution of the performance metric.
Exactly. It shows you the range of likely values for your metric, given the uncertainty from the missing labels.
Okay. Now the paper then dives into some theory behind this distribution.
Right. And a key observation they make is that many common classification metrics, accuracy, precision, recall, F1 score, can mathematically be written as sums or ratios of sums of these Bernoulli random variables, are imputed zeros and ones.
Ah, and that structure is important.
Very important because there's a lot of probability theory about sums of Bernoulli variables. This leads them to lemma 1.
Lemma 1, what does that tell us?
Lemma 1 is a known result, basically a form of the central limit theorem. It says that if you have a weighted sum of independent Bernoulli variables, that sum can be really well approximated by the Gaussian distribution, the classic bell curve.
Okay.
And they provide a bound on how good that approximation is using something called the Kolmogorov-Smirnov distance, which just measures the difference between two distributions.
And how does this apply to our metrics?
Well, metrics like accuracy and, as it turns out, precision estimators can be expressed in this sum of Bernoulli's form. So lemma 1 suggests that the distribution of accuracy or precision estimated via PMI should look roughly Gaussian.
Okay, so for accuracy and precision, the PMI distribution should be close to a normal bell curve. But what about things like recall or F1 score? Those are ratios, right? Like true positives divided by true positives plus false negatives for recall. That sounds more complicated.
It absolutely is more complicated. Ratios of random variables are trickier. This is where Theorem 2 comes in.
Theorem 2. What's new there?
Theorem 2 provides, apparently for the first time, rigorous bounds on how close the distribution of a ratio of correlated Gaussian variables is to another Gaussian distribution.
Whoa, okay. Why correlated Gaussians?
Because the numerator and denominator in metrics like recall or F1 often involve overlapping sums of the same underlying Bernoulli variables, our imputed labels, making them correlated. And we already know from lemma 1 that those sums might be approximated by Gaussians.
Ah, I see. So if the sums, numerator, denominator, are approximately Gaussian, Theorem 2 helps understand the distribution of their ratio.
Exactly. It lays out the conditions needed for this approximation to hold, like the average value of the denominator needing to be reasonably far from 0. You don't want to risk dividing by 0.
Makes sense. And then Theorem 3 builds on this.
Yes, Theorem 3 is really a central theoretical result of the paper. It gives a concrete, finite sample bound on that Kolmogorov-Smirnov distance again, but this time between the actual distribution of the ratio of sums of Bernoullis, which represents metrics like recall or F1 with missing labels, and a Gaussian distribution.
So it gives theoretical backing for approximating the distribution of recall or F1 score under PEMI with a Gaussian.
Precisely. It tells us, under certain conditions on the data and the pi values, that we can confidently use a normal distribution to represent the uncertainty in these more complex ratio-based metrics when labels are missing.
That's quite powerful. It justifies using a simple Gaussian curve even for these tricky metrics. And this theoretical foundation leads directly to PMI gas, right?
Exactly. Algorithm 2 introduces performance estimation by multiple imputation Gaussian approximation, or PMI Gauss.
And how is that different from the original PMI?
instead of doing all those thousands of sampling runs to build up the distribution empirically.
Right, the simulation part.
PMI-Gauss skips that. It uses the theoretical results, like Theorem 3, to directly calculate the parameters, the mean, and the variance of the Gaussian distribution that approximates the true distribution of the performance metric.
Ah, so it's analytical rather than simulation-based.
Correct. It leverages the theory to jump straight to the approximating Gaussian curve.
What are the advantages of doing it that way, using PMI-Gauss?
Several big ones. First, simplicity. A Gaussian is just defined by its mean and standard deviation, which is easy to understand and report. Second, analytical convenience. It's easier to work with mathematically if you need to do further analysis. Third, and perhaps most importantly, it's much, much faster computationally.
Because you're not doing all those repeated simulations.
Exactly. You just calculate the mean and variance formulas derived from the theory once. Big win for efficiency, especially with lots of missing data or large data sets.
Okay, that makes a lot of sense. Now, a practical concern. We talked about needing well-calibrated probabilities pi, but what if our calibration isn't perfect? What if those pi values are a bit noisy?
That's a very realistic concern, and the paper addresses it directly with Theorem 4. It deals with robustness to calibrator noise.
Theorem 4, and what's the verdict? How robust is it?
It's actually quite robust. Theorem 4 essentially proves that the main theoretical guarantees, particularly from Theorem 3 about the Gaussian approximation for ratios, still hold even if the true underlying probabilities, pi with a capital P, aren't exactly equal to our estimated pi.
Oh, under what conditions?
It holds as long as the true probabilities pi can be modeled by, say, a beta distribution that has the correct mean, our estimated pi, but allows for some variance or spread around that mean.
So as long as our estimated pi is correct on average, even if individual true probabilities fluctuate around it a bit, the method is still reliable.
That's the gist, yes, provided the fluctuation or variance isn't too large. Figure 3 in the paper gives a nice visual illustration of how much variation is allowed. It shows that the calibrator can actually be quite off for individual points, but as long as it's right on average and the variance is bounded, PMI-Gauss still works well.
That's fantastic. It means the method isn't super brittle. It can handle some real-world imperfection in the probability estimation.
Exactly. Makes it much more practical.
So theory looks good. It's practical. How did it actually perform in experiments? The paper tested it out, right?
They did. They ran a pretty comprehensive set of experiments using 6 real-world data sets. They trained standard XGBoost models, calibrated the probabilities using that scaling binning method,
Okay.
and then they simulated missing labels, both MTR, completely random, and MNAR, not random scenarios, at different missingness percentages.
And how did they evaluate PMI and PMI Gauss?
They used a few different techniques. One key method was the probability integral transform, or PIT. Basically, you see if the predicted cumulative distribution for the metric matches the actual observed values. If the prediction is perfect, the PIT values should follow a uniform distribution.
Ah, okay. So they measured how far the PIT values were from being uniform.
Exactly, using standard metrics like the Wasserstein-1 distance, W1, and the Kolmogorov-Smirnov KS distance to measure the difference in distribution shapes. They also looked at central tendency using root mean squared error, RMSE, and mean absolute error, MAE, to see how close the average prediction was.
Okay, lots of metrics. What were the key findings, say, in the MTR setting with maybe 30% missing labels?
The results were pretty clear, shown in tables 3 and 4. PMI and PMI-Gauss, when using the calibrated probabilities, generally perform the best. They consistently outperform baselines like just using Bootstrap on the data with complete labels.
And how did PMI-Gauss compare to the full PMI simulation?
The Gaussian approximation held up really well. PMI-Gauss results were often very close to PMI, sometimes even slightly better according to some metrics. It really validated the theoretical approximation.
Any other key takeaways from the MCR results?
A big one was the impact of calibration. When they used uncalibrated probabilities with PMI-Gauss, the performance dropped significantly. It really hammered home that getting good pi values is crucial.
Makes sense.
Also, interestingly, for metrics, just looking at the average error, like MAE, the difference between PMI-Gauss and the Bootstrap baseline wasn't always huge in the MCR case. But for metrics looking at the shape of the distribution, like W1 and KS, ignoring the missing data, like Bootstrap does, had a much bigger negative impact.
Okay, that distinction is interesting. What about the MNAR setting, missing not at random? That's often more realistic, but harder.
Right. Figure 4 shows some MNAR results.
Mm-hmm.
They also looked at how class imbalance, which they call PL, played a role. Generally, as you'd expect, performance was worse across the board in MNAR compared to MNAR.
Understandable. Any surprising results in MNAR?
A couple interesting quirks. For precision, especially with low class imbalance, the versions using uncalibrated probabilities sometimes actually did better than the calibrated ones.
Really? Why?
The authors suggest it might be due to the calibration method potentially overestimating probabilities in those specific tricky MNAR scenarios.
Huh. Okay. Anything else?
Similarly, for recall with low imbalance, the simple bootstrap method sometimes beat PMI Gauss. They thought maybe PMI Gauss was underestimating the recall in those situations.
So the MNAR results show it's still helpful, but maybe less consistently dominant, and calibration might interact in complex ways.
I think that's a fair summary. The MNAR setting just adds extra layers of difficulty. The key takeaway is still that PMI Gauss offer potential advantages, but the non-random nature of missingness needs careful thought.
So it really seems like the effectiveness depends on the metric, the missingness mechanism, MCAR versus MNAR, and definitely on having good calibrated probability estimates.
That sums it up nicely. The paper concludes that yes, these multiple imputation techniques, PNI and PMI Gauss, are valuable tools for evaluation with missing labels. But, and it's a big but a well-calibrated imputation model is absolutely crucial for them to work well.
But the good news is their experiments suggest standard calibration methods seem generally up to the task.
Yes, standard techniques like scaling binning seem sufficient in their tests, though they do caution that performance can vary by metric, so you should probably check how it works for your specific use case.
And did they suggest where this research might go next? Future directions?
They did. They pointed out a few interesting avenues. One is extending these ideas to cover a broader range of binary classification metrics, especially rank-based ones like average precision.
Okay.
Another is generalizing from binary O1 classification to multi-class problems, where you have 3 or more possible outcomes.
Makes sense.
And finally, applying these concepts to regression problems, where you're predicting a continuous number instead of a class label. That would likely involve different metrics and maybe different theoretical challenges.
Right, dealing with continuous outcomes could be a whole new ballgame.
Yeah.
Well, this has been a really illuminating deep dive into a genuinely important and maybe underappreciated problem in ML evaluation.
It really is.
It seems clear that when labels are missing, just ignoring them is often not good enough. It can really mislead you.
Definitely. And these methods, PMI and PMI Gauss, especially with good calibration, offer a much more robust, more nuanced way to understand model performance when you're, as the title says, evaluating in the dark.
Absolutely. And understanding that uncertainty, the range of possible performance values due to missing data, seems critical for actually monitoring and deploying models reliably in the real world.
It really does. Which leads to a final thought for you, the listener. How might getting a better handle on this uncertainty, the uncertainty caused by missing labels, change how you think about evaluating and monitoring your own ML systems? What other questions does this raise for your work, or just for your curiosity about how these systems perform in the wild?